So will 2026 be dominated by AI? Artificial intelligence has become central to almost all advances happening within the semiconductors and EDA, but will that continue throughout the year? Many opportunities and problems become highly interlinked in 2025, fueled by the historic growth in everything AI. But how close are we coming to the breakpoint? And what are people doing to mitigate them? That is the story that will unfold this year. The AI penetration into an increasing number of workloads is placing almost quadric demands on compute, memory, interconnect, and the architecture that bind them. Data centers designs are moving beyond just the performance considerations of GPUs. Issues such as power and thermal becoming primary design consideration all the way from the microscopic levels up to the national level and beyond. AI is coding the changing this that is increasingly helping to make those changes. 2026 could be a pivotal year, especially as we start to see production limitations and shortage developed in both semiconductor fabrication and packaging at the most advanced nodes and a limitation in the availability of the memory. We also could see a broad range of the companies benefit from the vast investment made by those on the cutting edge, which will be vital if the inference is to move out of the data center and into the edge. Continued development of the AI. Ask a dozen people to name of the most significant limiter for AI, and you will get a dozen's answer. Some of these are related to geopolitics and control on technology, on business issues, and we generally ignore those because nobody is willing to go on recording talking about this anymore. But there are many technical issues that people are willing to discuss, including memory availability and bandwidth, interconnect standards, and the need for new and more specialized data models, better security, and changing pressure from inference, among others. The biggest roadblock today is compute, said Baron Carr, CEO of Upscale AI. It's the networking portion. Systems can move data fast between the GPUs to keep up with the AI scale and speed. What exists today is proprietary closed technologies, and that this is making things more extensive and inflexible. The industry needs open standards so they can compute vendor if they adhere to the open standard and connect seamlessly. As companies start to rely on AI solutions, secondary issues become important. Memory safety has become the primary design requirement, said Jeff Viticci, CPU and Ampere Computing. The scale and sensibility of today's AI workloads mean that vulnerabilities, once considered niches, can now have the widespread impact. As organizers run high-value models concurrently, the risk of the memory corruption, data leakage, and exploitation increases sharply. In 2026, we expect memory-safe compute to move from an optional enhancement to a standard requirement, particularly for mission-critical AI operations. This year marks the turning point as memory integrity becomes a core expectation for any infrastructure built for AI at scale. The major driver has been large language models, but these are not ideal for many applications. We are seeing a lot of more research in small language models or domain-specific models, said Satis Balasubramanian, head of product management for AI and Solid Custom AI at Siemens CDA. They are focused on the training, taking a very simple open source models with 7 billion parameters and then fine-tuning it for the semiconductor domain. As the foundation models are getting smarter, people know how to build special models or the small language models. We are seeing an increasing focus on interferencing. As the focus turns toward the inference, design issues change. Inference adds further pressure with the low latency, high volume traffic from users worldwide, set of scalar car. Basically, your network has to evolve into a high-performance, software-defined fabric that is optimized for AI data centers and scale. The whole problem is becoming software defined. We see a lot of custom designs being built for a specific application, such as Balasubramanian. Everything is gonna be based on your workload or the end application, and then a software that determines the architecture decision, the PPA metric that are appropriate, or what process or tech node they need to focus on. We are seeing the more shift-left decisions being made, and they just give a lot of customization to workloads. We are seeing a lot of more design starts. Each workload has different needs. Enterprises are rapidly expanding the range of the AI workloads they run in production, said the Ampere Vitici. According to the recent McKinsey survey, more than two-thirds of respondents said their organization is using AI in more than one function. This expanding variety of highlighted that its AI workloads cannot be served effectively by a single type of compute. Each category of the model and even each individual component of a model has decisions around memory, latency, and cost and throughput. As some of those workloads become more stable, new types of optimization become viable. We see the people wanting to move away from the homogeneous architectures, says Carr. Today, people are locked into a single vendor because no one can interact with each other. If you want to do something different for pre-fill versus decode, use different hardware for one versus another. If you want to do the hybrid design, that's not possible. With the advent of the things like ESUN and UA link, you can mix and match. You might have one piece of hardware better than for certain things, and if you couple with a different piece of hardware, you might get better tokens per second. There are software programs in development that can enable these things. This could be a key change for 2026. Agentic systems accelerate the shift because they involve multiple tasks working with different resource profiles, making it harder to rely on a single type of hardware or uniform infrastructure footprint, said Wittist. In 2026, heterogeneous compute will become the defining characteristics of enterprise AI infrastructure. As the enterprises adopt the widening spectrum of workloads they need to support, and a mixed nature of tasks required with the workload. Data centers are also being impacted by more widespread adoption. Security is a big deal, says the Niels Fach, Vice President and General Manager, Keysight EDA. Customers want to run all of their tools within their own firewall. When we rolled out our first chatbot, which was hosted by Keysight, it went to go through the customer's firewalls and did not work for everyone. Rising AI demand, the need for performance consistency, long-term cost control, and stricter data requirements are pushing enterprises to rely on more infrastructure they directly control, said Wittich. Instead of depending exclusively on large centralized clouds, companies are building out regional data centers, regional data centers, and co-location footprints, and specialize on-prem deployment that are optimized for AI conference emerging agent workloads. This reflects a more balanced approach in which enterprises blend cloud capabilities with dedicated compute resources they operate directly to place workloads where they run most efficiently and predictably. So in 2026, we expect this blended strategy to mature as organizations refine their infrastructure models that use both closed and owned compute in complementary ways, allowing them to meet rising AI demands and greater stability and flexibility. More power indeed. During 2025, many alarm bells started to ring about power. This concern is at the die level, the package level, as well as the board and rack and data center and grid levels. Many AIS chips are limited by a thermal consideration due to the energy dissipation within the chips, while at the same time, fabrication and packaging density are increasing, resulting in higher power densities. This is causing the reconsideration of design practices that previously were thought to be too difficult. If you look at how crypto came into being, it went from CPUs and GPUs to GPUs, FPGAs, GPUs. And from CPUs to FPGAs to GPUs to dedicated chips. That's car. All of that was to reduce power and improve performance. Near threshold voltage is one way to achieve that. You will see a similar trend happening in the AI space. In order to adhere to these power needs or power bottlenecks, you will see those technologies come into play for AI workload-specific ASICs, as well as low-voltage ASICs. From the printed circuit board down to the die, power delivery networks are being examined closely. Different architectures are emerging, said Shekhar Kapur, Executive Director for Product Management and Synopsys. When you convert the 48 volt to 1 volt, or the data center for the data center, pushing hundreds of watts into a single port, you need to have power delivery very well planned. How are you gonna get from the voltage regulators to embedded voltage regulators, which themselves are going to the stack? The PMIC methodology is shifting from a general consideration of doing advanced package design with an interposer to a methodology where you address the performance per watt and reliable aspect of the you can stack as much you want. But if you do not have a plan, you're heading for problems. One of the first considerations to locating a new data center has become securing adequate power. Advancing toward artificial general intelligence (AGI) will require significant compute power, efficiency, and other solutions as Wittig. The models emerging today require far from a sustained compute than a previous generation, allowing the reliance access to the power needed for operate them. What begins as a rapid uptick investment throughout 2025 is now slowing down into 2026. The next phase of the AI development to bring a new level of the urgency edge enterprises and cloud provide extended latency capacity to support larger models, faster iteration cycles, and new forms of agentic and autonomous systems. In 2026, the race is about securing the compute and power infrastructure required to keep pace with the increasingly advanced generation. New technologies. AI will dominate the semiconductor industry cycles in 2026, much as it did in 2025. Leading to more challenges and disruption, the industry will continue to grow at a pace enabling it to reach $1 trillion by or even before 2030 with the aid of the AI in every facet of business and technology, said John Kibarian, CEO of the PDF Solutions. This fast AI-enabled growth comes with challenges, with the complexities associated with advanced 3D packages and system design and manufacturing, managing global supply chain complexity, and improving the operational efficiency. So we already see signs of combined industry-wide collaborative relationships between the design and manufacturing that leverage AI-based predictive analytics for boosting operational efficiency and smarter decision-making. What we started as a custom solution for each large customer is beginning to get consolidated. Look at the TSMC with COOP flow for 3D IC, said Balasubramanian. The methodology techniques that were developed and customized for one big customer, the customer 2, are being standardized into the ecosystem. We are at the stage. We are at that stage where it's gonna go mainstream. 3IC is mainly focused on the hyperscalers and the top of 3 or 4 semiconductor companies who are using it, because it's very complex and they have the money and they have demand and they have SKUs and they support the investment. But this is now trickling down to the other customers. This year is gonna be a big year for 3D IC, where it's gonna be a transition to mainstream. Synopsys Kapoor confirmed this last year. We said 50% of the high-performance computing design will be multi-die, and they had materialized for 2026. We expect that we grow another 20% to 25%. The reason is pretty simple. The big driver has been a training in the data center, and that is turning to an inference. When you start throwing in more videos and more agentic applications, having trained all these models, you need the ability to reload this information and infer from it. Some design will migrate it in-house. A lot of second-tier vendors who may not have the size, expertise, and deep pockets of leading guys to attack 3D ideas have been working through the ASIC vendor type arrangement, said Mark Sweeney, director of the product marketing at Synopsys. This arrangement allows them to have the chips done for them, or at least this last stage of the physical design. They will start migrating into their own team, so you will see a continued steady adoption. A lot of these companies have a pilot project with one more chiplets assembled together. That will continue to increase. The benefits are just too great. While it may not happen in 2026, we also can expect additional application arrays to start moving in this direction. We are seeing AI or Gen AI capabilities coming into mobile phones, said Balasubramanian. Once they have a requirement that they need to have these models, everything within a system, within a mobile phone, then they need to have enough high bandwidth. So while it may not happen in 2026, we also can expect additional application areas to start moving in this direction. We are seeing AI or Gen AI capabilities coming into mobile phone, said Balasubramanian. Once they have a requirement, they need to have these models, everything within a system, within a mobile phone, then they need to have enough high bandwidth memory, they need to have enough processing power. All of them must be within the limits of real estate, and they will drive toward a 3D IC. But the cost factor also comes into account. It needs to be cost-friendly for their customers to actually adopt it. That the whole idea of mainstream usage. It slowly trickles down from the advanced node and advanced technologies and major customers to the consumer side. That will probably be in the next couple of years. There may be additional challenges that need to be overcome before they can fully adopt the technology. A product at the mobile space has other components that they have to deal with, such as baseband, said Kapoor. They would be looking at a 3D heterogeneous integration. Inference is one thing, which may be their driver, but they have to enable, from a networking or a communication point of view, other aspects as well. Heterogeneous doesn't mean they need two different processor nodes. It is digital and analog, which will be part of the same package. The integration of the optics with the semiconductor has been around for a long time, but it's always been too expensive, too complex, or too niche to application. Co-packaged optics has finally come to a point where it's starting to be adopted for mainstream for a broadband application, especially with the data center driving the communication backplane between the data center, that is South Sweden. Enables you to get the communication between them fast enough, how and low power enough that they act as if they were a giant chip. By using optical connections between the board, it makes less difference whether they are processors on same machine or different machines. You bring machines closer together with a high-speed interconnection. New analysis. The migration to advanced packaging and assembly has brought that it's new physical issues that need to be understood. The applications become more complex, and you can talk about an application being purely electrical. Sedgwick cited fast. It's about circuit physics and maybe semiconductor physics, or it's mechanical. A lot of applications are now multi-physics, and now we know examples all about the thermal issues, especially when they are working on chiplet. When they look at the server racks, massive thermal issues cause mechanical stress. You now the need to do vibrational analysis on electronic systems. We've migrated from a world where you could look at engineering to spline at a time. Now we're live in a world that is about physics, multi-physics, and the need to coordinate multiple engineering the spline from product and design to product performance and reliability and manufacturability. This is going to create some interesting partnership. You will see some surprising solutions where unusual combination of components will come together because of the breadth of the solutions required, said Sweden. You will see an announcement being made where the companies that are traditionally in play and both multi-physics to chip-to-system solutions are looking for this chip-to-system solution. That should be interesting from a business side. Fascia sees a similar trend. It's a multi-engineering world, so you have to make sure that these workflows are all interoperable. That brings that with each number of challenges. You have to bring different tools, potentially from multiple vendors, together into one flow. Interoperability between tools is absolutely important. We'll see a shift from sometimes monolithic tools where you have one platform, one tool, and everything must happen in their environment. We have already seen some high-profile examples. The industry leaders are not only investing in these companies of shake-up growth. They want to get the technology they are investing in for the technological itself, said Kapur. You want to tap into that technology. It's just broadening your ecosystem beyond the traditional, secure your foundry capacity into how can I build a competitive advantage by partnering in some way. What started in 2025 is not the end of it. There will be more in coming years. Some issues need increasing levels of research. People will focus on semiconductor realizing the domain knowledge and the expertise and basics of science are getting more important. Physics, electrical engineering, electronics, said Balasubramanian. We are seeing a lot of research happening on it, but focus on semiconductor research, semiconductor design and manufacturing happening in the university. There is groundswell for getting good people trained. There is a talent gap that needs to be filled. AI is going to allow the experts to be experts and spend less time dealing with the intricacies of learning tools, Sherafase. As instead they can focus on requirement management design, that is a shift in the work of product development teams. At the same time, specialization continues to go up. It's very difficult for a company that is designing complex products to hire talent in the open market unless they can hire from someone who is in their space. There's going to be a lot of emphasis on internal development talent and internal training. You can hire good people from universities, but they are still novices, and a lot of companies depend on a critical talent, and so they will nurture the talent in-house. Bring people up to speed to has become the key. In IBS study, the industry willing to hire around 100,000 but can't find enough people, said Balasubramanian. People are coming in. New grads are coming in, but they need to focus on how to get ramped up. That's the whole idea of agent. They won't solve 100% of the problem, but if you solve the 20% of the problem that consume the 80% of the time, they can focus on the rest of the things, either to make a better design, the same design faster, or work on a multiple project. While some of these problems are causing delays and spin, functional verification continues to primary region, while chips are failing at increasing rate. Tools become better, and they allow consumers handle more complex problems faster. There are end market requirements that drive complexity, and they depend on better tools and instead data constant interaction. There's always gonna be a problem space where you feel like most complex problems cannot be handled as well as you would like. There are two reasons why chip fails: functional or physical. Physical is the most more regulated in terms of rules. It's much more than constrained with foundry PKDs, as well as Subramanian. Functional failures are where most issues happen. There is increasing focus on software development early in the chip design cycle, so that the software stack works very closely with the hardware stack and you cover all the corner cases. This is causing an increased demand for emulation. That may not work for the digital design, but struggles a more heterogeneous system. If you look at our company, we design hardware, visual instruments very fastly. We have very complex radios in some of these instruments. We don't design our chips in our turn. It takes several turns, and we've been at this for decades using our own design tools. We were very good designers. We use best-in-class practice. It's hard for us to get a writer at the first time with a 60 radius. If we go over 10 GHz, they create a whole set of the new technological challenges. You have different packaging technology, so the complexity is different. You're always dealing with the new frontiers of technology, and tools are enabling that. But it's constant race to make sure the tools can cover the complexity that customers deal with. Design practices. Design practices. AI will require new design tools and flow, and also will enable them. In 2026, AI's influence in design will expand there both vertically and horizontally, said William Wang, CEO of ChipAgent. Vertically, we'll see the AI-driven EDA evolve beyond the front-end and back-end stage, enabling the more automated and optimized full RTL2 GDS2 flows. Over time, the AI agent will begin to unify the feedback loops for the post-silicon validation back into a pre-silicon design, closing the gap between the simulation and real-world performance. Horizontally, AI extends its reach from digital design into analog and mixed signal domains, where data scarcity and complex interaction have historically limited automation. Together, these advances will reshape how designs are conceived, verified, and iterated, moving toward a truly intelligent end-to-end design ecosystem. While the impact of some AI tools had been disappointing and productivity boost with many EDA flow is large, agentic AI is going to revolutionize simulations, as Matt comments. Director of Product Management has synopsis, so the 2026 will be the year when it really comes out big. We already have some partners and companies are building agentic workflows. It's gonna take out all the mundane things we ask users to do and let them focus on design instead of simulation parameters. It is going to exponentially grow the amount of simulation that can be done. It will make software more accessible to engineers, no longer just a group who can fully leverage the technology. And we already talk about the simulation time, but a lot of time goes into setting up the simulation. That time can be more than a simulation, and that time is gonna get shrunk by a lot. Companies will need to be agile if they want to fully take advantage of these changes. Design houses will have to reorganize around AI augmented flow like AI Copilot, Agent for implementation, verification, and debug, said Carl. Next year, two things are gonna help. One is raise output per engineer, that is productivity. And the second thing is to improve the quality. More end-to-end platform integration with tight simulation iteration will push teams toward a more holistic code design with fewer tool silos. The competitive edge will tilt toward the people who can implement the operational learning groups. Can we capture the design and verification to continuously train models, which would improve the quality? Models of all types becomes increasingly important. We can think about building AI-generated models, and we can run a physics-based simulations, which can a lot of time, said Pashi. I think a lot of thermal analysis and electromagnetic analysis simulations, they can take hours, and you are optimizing, you are doing this many times over. If you do this upfront, you can build surrogate models, response services, and you use those in a simulation that can really speed up the design and simulation process as well. Methodology improvement has been significantly impacted by the lack of the models. If you create models by hand, you will always lose in terms of time, said Roland Junkin, head of department in the design methodology at Fraunhofer IIS Engineers Adaptive System Division. It's too slow, but those models are required for earlier evaluation and systems engineering. So how can you generate those models of general system description out of specification, out of requirement or something? This is the key for future. You need to find a mechanism that created those models out of the human description of what needs to be built. That's how the AI will help in this development process. If you learn from what has been done in the past, you can build new tools that solve problems. Shift left is powered by abstraction of problems from physical domain, said Proctor Narain, CEO of Real Intent. They show up because of these new technologies. If you have any problems in physics domains and you want to have a predictable design process, you have to bring the problem into a functional domain and make sure you have robust design techniques that will prevent those problems from occurring in the design. The understanding and modeling of the problem and the solutions get brought back into the functional domain. This will require all EDA components to create open interfaces. AI is a layer on top of these tools, said Fasse. Most customers want to combine different tools and some of their own capabilities, so they need standardization around the design practice, rules, and languages. For example, when it comes to languages, we are all using Python today. As more customers create Python-based software, workflows, they need to be able to infuse AI into that. No one company will be able to do it all. Phase 1 was more about targeted optimization and reaching a desired PPA in the fastest possible time, said Balasubramanian. The second wave is more general productivity improvement, focused on achieving outcome. It will address the issue. How can you become more productive if the complexity is increasing when your market window remains the same? That's where these assistants come into the picture. We are moving into the world of assistants, and for 3D IC will be even more enabler. In the past, you had to deal with many tools, many pieces, and this would help bring them together. RISC-V. While development around the RISC-V processor has slowed a little, this is only because it has evolved to a point where people can use it, gain experience with it, and slowly add the feedback into the development process. We are already seeing a rise in real workload silicon, the creation of V-side devices that are target specific workload processing, said Dave Karoff, CEO for Breakers verification system. RISC-V is tailor-made for this purpose, given its open ISA. This allows more traditional processes plus separate accelerators and the architecture to be replaced by a single core that contains the required data processing and control in one unit, with custom instruction to match. This trend will become evident in 2026 and will drive the new system-level verification requirement, along with the potential for AI to read a workload spec and design system around a fixed problem. RISC-V is catching up with the competition. We believe RISC-V is getting too bigger, especially with the geopolitics as Balasubramanian onion. People love open source, and open source at some point wins. Right now, we see RISC-V keeps getting better. RISC-V is in the same stage where the ARM architecture was 5 to 7 years back. Promising, but not as powerful as good as x86. That's why everyone is saying it just took some time. We are at the crux of RISC-V getting much faster. It's gonna get bigger. That's not going to stop. We are going to see a lot more design starts. Okay. Thank you for your time. See you next time.